we've had to do a lot of work to get to where we're at with determinants right now. And there are so many properties of determinants that I think it's useful just to sort of list all the major ones. So first of all, the determinant of any matrix can be expanded along any row or any column, right? So the determinant of a matrix, you can do this cofactor summation, right? You can choose any I you want and do the sum along a row, or you can sum across your row or sum down a column and choose your column A, I, J, right? So you can fix the first entry and sum across the second, or fix the second and sum across the first, right? Expand across any row or column, which is really nice. Second property, which is arguably even more important, the determinant of a product is the product of the determinants. So this really makes a lot of our more sophisticated determinant stuff work later on. Couple nice properties. Oh, this is supposed to be an inverse. Couple nice properties about matrices related to A. The determinant of an inverse is the inverse of the determinant, and the determinant of a transpose is the same as the determinant of the original. We saw that the determinant of any triangular matrix is the product of its diagonal entries, which is pretty easy to show once you know you can expand across any row. We also saw that a matrix is invertible if and only if its determinant is non-zero, right? Remember, we did this by analyzing the reduced row echelon form of A. But notice this is actually the thing that inspired us to invent the determinant in the first place. Our goal for the determinant was to come up with an easier way to detect when a matrix is invertible. And here, this says that we've done it. We've succeeded in finding a convenient calculation that tells us when a matrix is invertible. I guess that depends on how convenient you think cofactor expansion is. And then the final property is really equivalent to property 6. It's that the rows of a matrix, or the columns of a matrix, are linearly independent if and only if the determinant is non-zero. This is equivalent to 6 because if you have a square matrix, the matrix is invertible exactly when its rows are linearly independent. Or saying the same thing, the matrix is invertible exactly when its columns are linearly independent. So, determinant is non-zero if and only if matrix is invertible, if and only if rows are linearly independent. So that proves this last property. So, this gives us one more nice thing to do with the determinant. If you want to know if some vectors are linearly independent, you can just smash them all, well, as long as you have n vectors in Rn, you can smash them all into a matrix and then calculate the determinant of the matrix and see if it's zero or not.